Every time you start your car, or ride a bike, or even just walk down the street, there's a secret war being waged on a scale you can't even see. It's this hidden world of surfaces grinding against each other, a world of friction and wear, and the fight to keep things moving smoothly. Today, we're going to pull back the curtain on this world and explain the science of tribology. So, what in the world is tribology? Well, it's the official name for the science of surfaces rubbing together, and it really boils down to three key ideas that we're going to get into. Friction, the force that resists motion; wear, which is the damage that happens over time; and lubrication, which is basically our best weapon in this constant battle. To really get this, we need to zoom in, and I mean way in. Because no surface, no matter how shiny or polished it looks to you and me, is actually perfectly smooth. At the microscopic level, it's a totally different ballgame. Yeah, if you could shrink down and walk across any metal surface, it would look like a jagged mountain range. Seriously, these tiny little peaks are called asperities. And here's the kicker. When two surfaces press together, it's only these tiny peaks that are actually touching and carrying the entire load. Okay, so now imagine those two mountain ranges sliding past each other. Things get pretty intense fast. Those asperities smash and grind against one another, creating massive amounts of stress in tiny little spots. That's where friction comes from. And as this happens, little bits of material break off. We call these wear particles debris, and they act like tiny grains of sandpaper, just making everything worse. So, when these little peaks are under all that pressure, one of three things usually happens. First, they can bend elastically, kind of like a diving board, and then just spring right back. Or, number two, they can just snap off completely, or even plow a groove through the other surface. And finally, they can get permanently squashed out of shape. Think of it like smooshing a piece of clay. This brings up a huge challenge for engineers, right? If you can't see all this roughness with your naked eye, how on earth are you supposed to measure it and control it? After all, you can't fix what you can't measure. So let's see how they do it. Well, there are two main ways engineers talk about this. The first is called RA, which stands for average roughness. It's pretty simple. It's just the average height of all those microscopic peaks and valleys. The other one is RMQ, or the root mean square roughness. The math's a little more complex, but it gives you a different kind of picture. So you're probably thinking, okay, they sound kind of similar. Does it really matter which one you use? Which one actually gives you a more useful idea of what that surface is truly like? Well, it turns out that most engineers prefer RQ, and the reason is actually pretty cool. RQ is way more sensitive to any really big peaks or extra deep valleys. And here's the counterintuitive part. Deep valleys can actually be your best friend. They act like tiny little reservoirs to hold on to lubricant, and they give that nasty wear debris a place to fall into, keeping it out of the way so it can't do more damage. All right, so we've been deep in the weeds at the microscopic level. Let's zoom back out now and look at how all this tiny action affects the entire life of a part, from beginning to end. And engineers have a great tool for visualizing this, and it has a pretty funny name. This right here is the bathtub curve. And yeah, it kind of looks like one, right? It's a really simple but super powerful chart that shows us the chance of a component failing over its lifetime. You can see it breaks down into three very distinct phases. Let's start over on the left side, in phase 1. This is known as infant mortality. Right when a component is new, the failure rate is actually pretty high. This is where you shake out any problems from manufacturing or hidden flaws in the material. It's basically the break-in period. Then, after those early failures are weeded out, we drop down into the bottom of the tub. This is phase 2, or normal life. This is the good part. The failure rate is super low and stays pretty flat. This is the long, reliable service life that the engineers were designing for in the first place. But, of course, nothing can last forever. Eventually, we start climbing up the other side into phase 3, the wear-out phase. All that microscopic damage we talked about has been adding up over time. The surfaces are degraded, and the failure rate starts to shoot up. And you can often sense this happening. Things get noisier, they start to vibrate, and parts might feel a little loose. So how do we fight back against that wear-out phase? How do we stay in that nice, flat part of the bathtub for as long as possible? Well, our single best tool is lubrication. But it's not just about squirting some oil on it. It's about finding that perfect balance, that lubrication sweet spot. And to find that sweet spot, engineers use a really critical number called the dimensionless film parameter, which we show with the Greek letter lambda. It sounds complicated, but it's a really simple idea. It's just a ratio that compares how thick the lubricant film is to how rough the two surfaces are, and that one number tells you everything you need to know. And as you can see, lambda is king. If your lambda value is less than 1, you're in what's called boundary lubrication. This is the danger zone. It means your oil film is too thin, and those asperities are crashing into each other. If lambda is between 1 and 3, you're in mixed lubrication. You've got a partial film, but there's still some contact. But the goal, the absolute holy grail of lubrication, is what we call hydrodynamic lubrication. That's when lambda is greater than 5. Here, you have a nice, thick film of fluid that completely separates the two surfaces. They literally never touch, and that means you get the lowest possible friction and wear. Okay, so we've covered a ton of ground here, from microscopic mountain ranges to bathtub curves. Let's wrap this up and talk about why this deep dive into the world of tribology is so incredibly important. Here's the real takeaway. Getting a handle on this hidden world of friction isn't just some abstract science problem. It's absolutely fundamental to making sure that pretty much every machine we rely on, from our phones to our power grids, is reliable, efficient, and lasts as long as it should. And these ideas we've talked about are the real-world tools of the trade. The bathtub curve isn't just a chart in a textbook. It's the playbook engineers use to predict when things will fail and how to make them last longer. Understanding lubrication lets them build things that run smoother and use way less energy. And that kind of brings us to one final thought. As our technology just keeps getting smaller and faster and more complex, these challenges of friction and wear, they just become even more critical. It really makes you wonder, doesn't it? What new frontiers in medicine or computing or space travel are going to be unlocked next, all by mastering this fundamental science of surfaces?